All right, welcome back, everybody. This is going to be, I believe, lecture 30 of Chemistry 352. And we are going to be talking today about amino acids, peptides, and proteins. This happens to be my very favorite subject of all. So some of the things that I will tell you about are not necessarily included in the text, and I'll try to make it clear when that happens. But my goal for you is to be able to understand the world of peptides and proteins at the molecular level. And to do that, we're going to begin with talking about what a protein or a peptide is. And then we'll also talk about the 20 proteinogenic or canonical amino acids. So with that in mind, let's get started. A peptide or a protein they are both polyamides, and they are oligomers of amino acids. Peptides tend to be sort of less than 50 amino acids long, whereas proteins tend to be somewhere like greater than 30-ish amino acids long. So there's some overlap in between what people will call a peptide versus a protein. Let me just draw for you the structure of the basic structure of a peptide or a protein. We're going to start with a squiggly line here indicating that we're taking a look, a snapshot of a shorter segment of a protein. Here is a nitrogen. Here is a carbon. There's another carbon. And that is one amino acid. We're going to call this the carbonyl carbon, this the alpha carbon, and then we'll just call the nitrogen the nitrogen. Most amino acids have a side chain at the alpha carbon and a proton at the alpha carbon. And then the carbonyl carbon for one amino acid is attached to the nitrogen of another amino acid. And that nitrogen is attached to the carbonyl carbon via an amide bond. Don't quite like how I drew that. Okay. So I'm highlighting in orange the first amino acid, and in purple I'll highlight the second amino acid. And the bond between amino acid 1 and amino acid 2 is called an amide bond, or is sometimes called a peptide bond. So I guess I'll highlight that in gray. And so we'll often call, I guess we're going to need just a little bit more space. We'll often call this the amide nitrogen. This we'll call the alpha carbon. And this we'll call the carbonyl carbon. And this we'll call the carbonyl oxygen. Together, those atoms define what we will call the peptide backbone. And this is important because we're going to see that the backbone of peptides and proteins consists of repeating amide nitrogen, alpha carbon, carbonyl carbon, then amide nitrogen, alpha carbon, carbonyl carbon, and so forth. So sometimes we'll talk about amino acids being a certain distance apart from each other. This orange amino acid, we're going to call it the I position. Just any arbitrary starting counting point. The purple one would be I plus 1. So the I plus 1 amino acid is attached to the I position amino acid through an amide bond between the amide nitrogen of I plus 1 and the carbonyl carbon of the I position, and so on. And so we might continue on. Here is another amide nitrogen, here's another alpha carbon, here's another carbonyl carbon, and here is another side chain. I will eventually stop showing the protons on the alpha carbon that are there, but are going to be implied instead of shown. Notice that all of these amino acids have the same stereochemical configuration. That is, if you were to assign R versus S, you would get the same stereochemical configuration of each of these alpha carbons. And we'll just leave a squiggly line at that. Oops, at that position. So we can see that a peptide or a protein is a linear polymer of amino acids linked together by amide bonds. So here's an amide bond, here's an amide bond, here's an amide bond, and so on. Okay, and of course, I suppose the green amino acid we would say is at I plus 2 relative to the orange one, and then I plus 3, and then I plus 4, and so on. So this is the basic structure of peptides and proteins. They're each composed of a linear chain of alpha amino acids. We call them alpha amino acids because the nitrogen is attached to the alpha carbon. There is one carbon in between the nitrogen and the carbonyl carbon. Notice also that the alpha carbons in general, notice also that in general the alpha carbons are stereocenters. So peptides and proteins are chiral, and the stereochemical configuration of the side chain along with its functional groups is going to control the kinds of shapes that a peptide or protein can adopt. All right. So I want to talk a little bit about, before we even worry about what the side chains are, I want to talk a little bit about the shape and structure of peptides and proteins. All right. And to do this, we're going to focus in, I think, on just the purple amino acid and the amino acids that are in front and behind of the purple amino acid. All right. I guess I'll have to touch that up a little bit. Sorry. Copy and paste errors. I guess it would have been quicker, you guys, if I had just drawn the whole thing from scratch instead of trying to erase the parts of it that I no longer wanted. But live and learn, I suppose. You're always welcome to fast forward through the silly and inane things I do while I'm drawing things. Oh well. And sure, I think we still want to highlight things. All right. So let's do a couple of things. Let's talk about, notice that the peptide backbone involves sigma bonds between the carbonyl carbon and the amide nitrogen, the amide nitrogen and the alpha carbon, the alpha carbon to the carbonyl carbon, and so on. Okay, so those are these three sigma bonds associated with each amino acid. Let's talk about conformations of this peptide or protein about that sigma bond. So to do this, we're going to do a Newman projection, looking down the carbon amide nitrogen bond. Okay, now let's talk about the features of that amide bond between the carbonyl carbon of the orange I position amino acid and the nitrogen of the purple I+1 position amino acid. If you were to look at that nitrogen and ask what is its hybridization, what would you say? Go ahead and take a guess, commit to it. If you said sp3, you might have been thinking of the fact that that nitrogen has lone pair electrons on it. And that is a reasonable assumption. However, resonance tells you that those lone pairs on that amide nitrogen can be delocalized, donate into the carbonyl carbon to form a pi bond between amide nitrogen and carbonyl carbon. So it turns out that because of resonance, both the carbonyl carbon and the amide nitrogen are sp2 hybridized and are trigonal planar. Now what that means is that if we were to look down the bond between carbonyl carbon and let's see, orange carbonyl carbon and purple amide nitrogen, what we would see would look like this. Here's your carbonyl carbon. We'll just put alpha carbon here and carbonyl oxygen here. It's trigonal, that carbon is trigonal planar. We're looking at it on the side, and then in the back, which we can't see the nitrogen, we would see a proton here and then the alpha carbon here. And this amide is in sort of a trans orientation because the two alpha carbons are anti to each other. So this would be the trans conformation. But you might also imagine that another conformation might exist. This would be one in which the alpha carbon in the front is cis to the, or eclipsed with the alpha carbon in the back. And we would call that a cis conformation. And these are the two conformations that are possible for about the sigma bond between carbonyl carbon and amide nitrogen. If we were going to measure a dihedral angle, we might say that the angle between alpha carbon, orange alpha carbon and purple alpha carbon is 180 degrees here, whereas it is 0 degrees here. You've got those two possibilities. Why wouldn't other possibilities be possible? Well, if you imagined twisting the nitrogen in the back, starting at the trans conformation, imagine grabbing onto that alpha carbon in the back and twisting it in a clockwise direction, you would have this intermediate sort of structure where you would have broken resonance overlap or conjugation between the carbonyl carbon and the amide nitrogen. And that's energetically costly. And so because of that, this would be a high energy transition state, not an allowed intermediate. Okay, in other words, the carbonyl carbon to amide proton sigma bond has partial double bond character, and like double bonds, rotating about double bonds has a really high energy barrier. All right. Now let's talk about the dihedral angle possible about the bond between amide nitrogen and alpha carbon. So to do that, we're going to look down the bond between nitrogen and alpha carbon. It may help us to copy this again just so that we know what we're looking at. All right, so in the front we have the amide nitrogen, which we've said is trigonal planar. So here's the alpha carbon. In the back where we can't see it is the alpha carbon, and that alpha carbon is sp3 hybridized. So it's going to have three things coming off of it. Now, in the way we've drawn this peptide in its extended form, in the back we would have the carbonyl carbon pointing downward, coming out. Let's see how I might draw that better. Coming out to our right would be the side chain, and coming out to our left would be the proton. And the dihedral angle we're going to use to describe conformations about this bond is the dihedral angle between the alpha carbon to nitrogen bond and the oops, sorry, that should be the previous carbonyl carbon there. So this is going to be the bond between carbonyl carbon at the I position and the amide nitrogen at the I+1 position. And then in the back, it's going to be the bond between the alpha carbon in purple and the carbonyl carbon in purple. All right. So this is the I position amide nitrogen, or carbonyl carbon. This is the I+1 amide nitrogen, the I+1 alpha carbon, the I+1 carbonyl carbon. All right, and we're looking at the dihedral angle between this bond, highlighted in red, and this bond. We're going to give that dihedral angle a name. It's going to have the name of the Greek letter phi, and phi can adopt many different values. And in fact, we might expect it to range from -180 to 180 degrees. And the thing that's going to influence what that dihedral angle is the size and identity of the side chain, this R group. Okay, you might imagine looking at this bond that if the R group is large, you might prefer that purple R group to be as far away from the orange carbonyl carbon as possible. So as an example, we would need to consider, I think I want to just copy this. And let's just imagine the situation in which the R group was the biggest thing. It's possible that this conformation would be preferred with a much different dihedral angle between the two bonds that are shown in red. Okay, so there are many different possible angles for phi, and what angles they are is going to depend on what the identity of the R group is. Now, let's take our same peptide drawing and talk about the third bond. And this is going to be the bond between alpha carbon and carbonyl carbon. We'll talk about rotation about that bond. We're going to put our eye in the plane of the page and look down the bond between alpha carbon and carbonyl carbon. All right, so I'm going to draw in front the alpha carbon. As we've currently drawn it, the amide nitrogen would be pointing down, and the side chain R would be coming up to our right, and the CH, the alpha proton, would be coming off to our left. And the way we've drawn this molecule now, you would have the carbonyl oxygen eclipsed with the amide nitrogen. And then in the back you would have the green amide nitrogen from the I+2 amino acid. All right, and the dihedral angle we would be interested in would be this angle between the two red lines here. We're going to call that dihedral angle Greek letter psi, and that's going to be the dihedral angle between sigma bond between amide nitrogen and alpha carbon and sigma bond between alpha carbon, carbonyl carbon and amide nitrogen of the I+2 amino acid. Okay? And of course, you might expect there to be many possible values of psi ranging from -180 to 180. For example, we could take our same drawing and we can keep the alpha carbon in the front exactly the same. But what if the side chain R is the biggest thing on alpha carbon? Then you would want the rest of the peptide chain connected via amide nitrogen at I+2 to be trans or anti to the R group, and so you would get a much smaller value of phi there. And of course, the size of that side chain and its functional groups are going to determine what that psi dihedral angle is. All right. So what do we care about dihedral angles anyway? We're going to see that the conformations adopted by individual amino acids determine the overall shape of the molecule. So what we're going to do now is look at the structure of an amino of a helix, of a peptide helix. And what I'm showing you is the structure of a helix bundle from the yeast transcription factor GCN4. This is a ribbon diagram where the blue ribbon shows you roughly the trajectory of the peptide backbone. So I'm going to try to simplify this diagram a little bit. All right, so I'm doing this now on my computer, which will give us more control than the iPad did. I'm showing you now a peptide called EYK. It's one that we made in my lab, and it's one that forms a triple helix bundle, a three-stranded helix bundle, 3 helices wrapped around themselves. Now this is called a ribbon diagram, and the ribbon or cartoon that you see circling back and forth simply represents the trajectory of the peptide backbone, that amide proton, alpha carbon, and carbonyl carbon. And these 3 helices interact with each other. And if we look down the axis between the helices, we can, and then we start to take a cross section, we can see we can move down the helix and see each of the individual side chains as we progress down the helix. One of the things we can notice here is that you tend to have non-polar amino acid side chains in the middle with polar amino acid side chains on the exterior. Now, we haven't talked about polar versus non-polar amino acids yet, so it's okay if that's a little bit weird. I'm going to turn off the ribbon. Let's see, hide cartoon. I'm also going to hide the side chains to simplify things for us. And I'm going to choose 3 amino acids. One of them we're going to color, what was it, orange. The next we're going to color purple. And then the last we're going to color green. All right, and then I'm going to hide everything, and I just want to take those 3 amino acids and show, well, we'll just show all of the sticks. All right, and we're going to center in on the purple amino acid like we had done previously. All right. So looking at that purple amino acid, you have the amide nitrogen here. Let's see, we can get it so we can select atoms. The amide nitrogen here, the alpha carbon here, and the carbonyl carbon there. And that is the, I guess, I+1 amino acid. This would be the I position amino acid, carbonyl carbon, alpha carbon, and amide nitrogen. And then over here, the I+2 amino acid, amide nitrogen, alpha carbon, carbonyl carbon. And the other things are side chains, but we're going to focus in on the backbone. So let's do what we did in Notability, but let's look down. We're going to center and orient things We're going to look down that bond between carbonyl carbon of the I position residue and amide nitrogen of the I+1 position residue. And you can see that the bond between I+1 nitrogen and alpha carbon is trans, or anti, to the bond between alpha carbon and carbonyl carbon on the I position residue. And we can actually measure that dihedral angle in this program. And it will tell us what that angle is, and it's pretty well close to 180 degrees, which is what we expect because of its partial double bond character. Now let's look at the bond between the I+1 position nitrogen and the I+1 position alpha carbon. And let's look at rotation around that bond. Here you can see that the bond between I position carbonyl carbon and I+1 position nitrogen is gauche to the bond between alpha carbon and carbonyl carbon of the purple I+1 position residue. So we can actually measure that dihedral angle here. And to do that, we need to click on the atoms that are involved in this Newman projection. And we see a dihedral angle of -66. There's a sign convention that determines whether that dihedral angle is positive or negative, and you don't need to worry about that now. Similarly, we can look at rotation around the bond between alpha carbon and carbonyl carbon of the I+1 residue. If we look down that bond, we would be looking at the dihedral angle between this I+1 position nitrogen and the alpha carbon, with the bond between carbonyl carbon and I+2 position nitrogen. And that dihedral angle is -34. So we can go through and do similar things for each of the amino acids in this peptide. And if we did that, let's just do the same thing for the orange amino acid. Let's look at rotation around the bond between amide nitrogen and alpha proton. Dihedral angle of -60. And then the bond between alpha carbon and carbonyl carbon, dihedral angle -47. And you can see that this first dihedral angle, phi, for the orange residue is close to the dihedral angle, close in magnitude and sign to the dihedral angle phi for the purple amino acid. And similarly, so this is the phi angle, the first one, and then the second one is the psi angle, -47 versus -35. They tend to fall in similar ranges. And if we went and measured these dihedral angles for the whole peptide, what we would discover is similar phi values for each amino acid and similar psi values for each amino acid. And as we continued on from amino acid to amino acid in this protein, what we would see is that there are groupings of phi and psi angles in the sort of -60 and then -45 range, that if you have a string of amino acids all with those dihedral angles, you tend to get a particular shape, in this case the helical secondary structure. All right, now we will do a similar analysis with a slightly different looking protein. It's taking a minute to search. There we go. So here is another protein, another one we work with a lot in my lab. I'm going to color all of the side chains the same. Shoot, I don't like that color. Let's go here. All right, I'm going to hide the ribbon diagram. The arrows indicate that this is a beta sheet protein, where the arrow indicates one of the strands of the beta sheets, and we'll talk more about that structure later. I'm going to hide the cartoon, and I'm going to hide the side chains. I'm going to show the main chain sticks. And we're just going to look at the phi-psi angles for say this amino acid, and this one, which will color, what was it, purple, and then the next one, which will color green. All right, so let's measure the phi and psi dihedral angles as we did with the protein that was helical. So we'll measure the dihedral angle about the bond between amide nitrogen and alpha carbon. And in this sheet context, that angle turns out to be minus 150. That's way different from where it was in the helix. We measure, so that's the phi angle. Let's measure the psi angle for the same residue. Also about like minus 180. So again, those two dihedral angles are way different than we saw in the helical protein. And if we continue on to make measurements of these same phi and psi angles in these successive amino acids, what we will see is that they all tend to adopt larger, greater or less than 100 degrees in dihedral angle. Oops. And so you can see, compared to what we saw for the orange, purple, and green amino acids in the helical protein, we've got quite a different situation than for these orange, purple, and green amino acids in the beta sheet protein. What I'm trying to communicate, probably not that successfully, is the idea that the phi here and psi dihedral angles of each amino acid determine the shape of the molecule, and that a sequence of amino acids with similar dihedral angles can be responsible for the types of shapes that proteins form. In this case, This shape is called a beta strand, this sort of extended zigzag shape, whereas the other shape I showed you was a helix. So with that, we've talked about how rotation around the carbon-nitrogen bond, the nitrogen to alpha carbon bond, and rotation around the alpha carbon to carbonyl carbon bond, described by dihedral angles phi and psi, respectively, can tell you something about the structure of a peptide or a protein, and that extended sequences of amino acids that adopt similar phi and psi values, respectively, can lead to regular types of shapes that you may have recognized before in proteins, the alpha helices and the beta sheets. So at this point, students often ask, what do we need to know? What do I want you to memorize? Well, I need you to know the definition of the phi dihedral angle and the psi dihedral angle. And I need you to have in your mind the idea that the values of those angles determine the overall shape of the peptide or protein. I also need you to be able to recognize amide nitrogen, alpha carbon, carbonyl carbon, and oxygen. And I need you to be comfortable looking at successive amino acids in a sequence. Next time, we'll talk more about what the side chains are and a little bit about how those side chains influence the structure of a peptide or a protein. Until then, have a great day, stay healthy, be safe, and I need a good sign off. I'm trying to think. Happy trails? No. I got nothing. In any case, we'll see you next time.